All right. Do you think we need a review of the chapter from last time, or should we start the questions right away?
No, I think we can start.
Okay. So let's do some warm-up questions first, and then
Mhm.
we'll move on to the difficult ones. So, which statement about Newton's second law of motion is correct?
Okay. C.
Yep, that's right. Excellent. Constant mass, resultant force proportional to acceleration F equals ma. Okay, next.
Yeah.
Which one's not true about friction?
Okay. Uh,
Mhm. If at any point you want us to do a question together, please feel free to let me know, okay?
yeah. It
Can
should be D, I think. Oh, sorry, it's not true. It's C, I
yes,
think. Yeah.
yep, excellent. And do you prefer to read the question yourself, or would you like me to read it instead?
Maybe you.
Okay, okay. All right, so for a stationary object, force due to coefficient of dynamic friction is. Oh, wait. Okay, so I want you to justify your. Oh, it's not true. Yeah, that's right. Yep, that's right. Because if it's stationary, there is no dynamic friction, so
Mm-hmm.
that is zero. All
Yeah.
right, so which statement best summarizes Newton's first law of motion? When two objects interact, forces exert equal and opposite. Resultant force of an object is equal to the rate of change of momentum. A body will remain at rest or move with constant velocity unless acted on by a resultant force. Or part D, a body will move in a constant velocity only if there is a resultant force acting on it.
Uh, yeah, it should be C.
Yep, that's right. Excellent. Which statement about drawing a free body diagram is not correct? Arrows must be drawn to scale and represent the size of the force involved. All force arrows must originate from the object upon which the force is exerted. Force arrows must be drawn in straight lines with a ruler, or force arrows do not have to be labeled.
I think.
Mhm. Did you say an answer?
Yeah. Did it cut off?
Oh, yes, it did. Sorry. Could you please repeat that?
Oh yeah. It's D.
Yep, that's right. You need to label them.
Yeah.
And we'll see a question for this soon. A free body diagram is simply drawing all of the forces on your diagram so that you can visualize them and then equate the opposite forces or figure out the unknown forces, okay?
Okay.
All right. So this is something we did not do last time. That's why I included the questions here so that we can cover this as well. So let's do a quick review of uniform circular motion or circular motion. I think we did this in IGCSE as well. So if you recall something, you're very welcome to contribute.
Mm-hmm.
Okay. So if you have an object, let's say you have a trolley and it's moving in this direction with velocity v. Okay.
Yep.
Now, if you apply a force that is perpendicular to this velocity, like that, so let's say this is the force F, then you're going to change the direction of motion, right? instead of going like that, it's going to move a little bit in this direction now. Is that intuitive?
Yeah.
And let's say the trolley is here now, and it's moving in this direction with velocity v, and you apply a force perpendicular to it again, like that. Then its pathway will be curved once again like that. Is that clear?
Yeah.
So basically the idea is that if you have an object moving in a certain direction and you apply a force perpendicular to its direction of motion,
Mhm.
it starts moving in a circular path, okay? And if you apply a force that is constantly perpendicular to the direction of motion, then the object starts moving in a perfect circle, okay? So
Yeah.
that uniform circular motion. So the condition for circular motion is force perpendicular to velocity. So whenever you have force perpendicular to the velocity vector, you will observe circular motion.
Okay.
Now, whenever an object is moving in circle, let's say this is your circular pathway, the force, the resultant force is always towards the center of the circle, like that, okay? Wherever you are or wherever the object is along its path, the resultant force is always towards the center of the circle, and we call it the centripetal force, okay?
Okay.
So in circular motion, resultant force, it's called the centripetal force, and it's towards the center of the circular path. Circular path.
All right.
All right, next are a few formulas. Okay, so there's one more thing to understand before we move on to the formulas. It's the first thing is that if you have a circle, the circumference, we can call it S, okay?
Yeah.
And that is equal to, so the actual distance is your circumference, right? And the distance from the center to the boundary or center to circumference is your radius. Is that clear?
Yeah.
Now, when you're moving in this circle, what you're essentially doing is sweeping some angle, right? Let's say
Yeah.
you start at this point and you end at this point for now, right? So what you're doing is you are covering some distance s, but you're also sweeping some angle theta, right?
Mm-hmm.
This angle theta is called your angular displacement, okay? And
Yeah.
the relationship between s is your arc length, okay? S is your arc
Mm-hmm.
length, and theta is your angular displacement. The relation between these two is this. S is equals to r theta. You need to memorize this formula.
S is equal to R
Yep.
and theta. Okay.
Yes.
So if it's in degrees and it's like 40 degrees, you
Uh,
just times it by 40.
your theta needs to be in radians for this one.
Okay. So if it's like,
Mhm.
I don't know, I don't know, 2 pi over
Yes.
4 or something like, I don't know.
Yep. Yep.
Okay.
So the condition for this is that your theta must be in radians, and you should know how to convert degrees to radians.
Yeah, okay.
Degrees to radians.
You times it by 180 over pi, right?
Yep.
Okay.
All right, so you are right. Then multiply pi over 180. So to go from degrees to radians, you multiply your degree value by pi over 180.
Okay.
If you don't want to learn this, if you should not, but if you happen to forget this number, you can always use the ratio method, like degrees ratio radians, right? In 180 degrees, 180 degrees is 1 pi radian, right? Or
Mm-hmm.
360 degrees is 2 pi radians. So if you have your answer in degrees, let's say you have 200 degrees, and you want to find out the radians like that, you'll just cross multiply that. So you have x into 180 or 180 x over 5. Let's see. 180x is equals to 205.
Mm.
So you set up a ratio and then you cross multiply them.
Okay.
180x is equals to 205, and x would then be this 200, which is your value in degrees, multiplied by 5, and this 180 from the left-hand side goes to the right-hand side to be and gets divided over
Okay.
180. So the shortcut you can learn is if you want to go from degrees to radians, whatever number you have in degrees, you multiply that to pi over 180 like that. So that's your shortcut. And if you happen to forget this number, you can always use your degree to radians ratio to figure that out.
Okay.
Okay?
Yeah.
So the first important relationship is S is equals to R of theta. The second important thing here is this conversion factor of pi over 180. And if you want to go from radians to degrees, you just have to do it the other way around.
Okay.
Yeah. So it would just be multiplied by 180 over pi.
Okay. Or you can divide it by pi
Yes.
over 180.
Yep, that's right. Or you could just divide that by pi over 180. Excellent. All right, so once we understand this relationship, we can move on to the next stage, which is velocity. Now, again, I'm just going to draw the same circle. If you're moving along a circle, you have something called the tangential velocity, right? The
Yeah.
tangential velocity v is the velocity tangential to the circle, okay?
Mm-hmm.
And we said that there in the previous circle, you saw that there is something called angular displacement, which was how much angle you're sweeping, right? The
Yeah.
amount of angle you're sweeping. In this case, we have something similar, which is how much angle you're sweeping per unit time. Okay? Because what you can think of is that the displacement got translated to velocity, right? Instead of displacement, you now have velocity, which is the rate of change of displacement, right?
Yeah.
And instead of angle, you now have angular velocity, which is the rate of change of this angle. So all
Yeah.
you did was divided both of those terms by time, and you have v and omega. So what was the relationship? What was the first relationship? S is equals to r theta.
Yes.
So you divide S by time, and you divide theta by time, and you end up with v is equals to r omega. Is that clear?
R omega. Okay.
So this is
So
a
and omega is the angular velocity.
yes,
I
angular
mean, not
velocity.
the omega over time.
So this is theta. theta or
Sorry,
phi.
yeah. Omega, sorry, the omega.
Yeah. Omega is rate of change of angular displacement, or theta over time. It's right here. Right. Next, we have something called. So I would, instead of deriving it, just help maybe ask you to learn this. There is acceleration is v squared over r. So your centripetal acceleration has this formula, v squared over r. And if you plug in this v here, so this formula you need to learn. And then there's the second formula that you can derive. If you plug in this v in that formula, you end up with acceleration is equals to, instead of v, I'm going to write r omega. And that whole term will be squared over r. So that would be r squared omega squared over r, and then the r's cancel out, and you have r omega squared. So the second formula for centripetal acceleration is omega squared r.
Um, 1 second.
Yep, sure.
Sorry, it was
Oh, no worries
the
at all.
the hotel cleaner.
Okay, no worries. All right. Okay, so are we good with the second formula?
Yeah, so basically to find the acceleration of the what acceleration are we finding exactly? The centripetal
Yes.
acceleration. Okay.
Mhm.
So you just dividing the velocity and okay, fine, okay.
Yep.
Yeah, I think yeah, okay.
Right. There is a derivation for that as well, but I don't think it's in your syllabus. I'm just skipping the derivation of the first one. But you should know where the second one comes from. It's just the plug-in of this formula into your first centripetal acceleration formula, and you end up with this one. Sounds
Yeah.
good?
Oh, one thing, so in the like initial like velocity equation where it's like rw squared, does the r also get the square or no? It's just the w, just the omega.
In this equation?
Yeah.
In this equation, nothing is squared. I just put that like as a label, second equation.
Okay.
So, quick recap, you had S is equals to R theta. You divided S by time, and you divided theta by time. So
Yeah.
you get V for this one, and then R stays the same, and theta by T is omega.
Okay.
Is that better now?
Yeah, that's better.
And then you have centripetal acceleration, which is V squared over R, and you plugged in your second equation into the third one, and you end up with the fourth one.
Okay.
Okay, and the fifth and final equation is Newton's second law that will apply to this concept of circular motion. So Newton's second law just says that force is proportional to acceleration.
Thank you.
So
Thank
you
you.
have F is equals to ma. So basically, this is just Newton's second law, which says that force is proportional to acceleration, and we know that to remove the sign of proportionality, you need to introduce a constant. So
Yeah.
turn this proportionality into equal sign, you introduce a constant, and that constant in this equation is your mass. And simply, you can plug in any one of these two acceleration formulas in this to get your centripetal force formula. So your centripetal force can
This is
be
m
M.
times one of the two.
Yes. It
Okay.
can be mv squared over r, or it could be m omega squared r.
Okay.
Where
So it's basically just using like one new equation and inputting it into different like
yes,
equations we already had, like F equals ma, um, S over T, and so on. Okay.
yes. Yep, that's right. So these were all of the equations. If you'd like to take a look, you're very
Yeah.
welcome. Otherwise, we'll move on to the questions.
Yeah. And the first one we had to know was R times omega, times theta.
S is equals to R theta.
Yeah.
This was the first one.
Okay.
All good?
Yeah, yeah, that's fine.
Okay, let's move on to the questions. So, in uniform circular motion, which of the following is incorrect?
Okay.
Magnitude of the velocity is constant. Direction of the velocity is constant. Centripetal force is towards the center of the circle. Centripetal force is 90 degrees to the velocity.
It's B.
Yep, that's right. If it's moving in a circle, of course, it's changing direction at every instant.
Yeah.
Okay, perfect. Next, a child whirls a conker on a string around their head. The conker moves with uniform circular motion. The linear speed of the conker is 5 meters per second, and the radius of the circle is 0.5 meters. Calculate the angular speed of the conker.
Okay. So a conquer
It's I think it's
is
a seed. I am not sure, but I think it's the chestnut seed. You could think of it wrong.
okay. 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 Um. So the speed is 5. Radius is 0 point. Okay. So the equation for angular speed equals um. I remember. Wait.
Mhm.
Um. Is fate over t? What?
You are on the right track, but that was a part of the derivation. We would rather use the direct equations now, right? So the equation was V is equals to R omega, and
Okay.
you could rearrange for omega, right?
Okay. Yeah. I guess. Okay. So you do 5/0.5,
Yep,
which is just 10.
yep, that's right. Very good. See. What's an angular displacement of 5/6 radians in degree?
Okay. You times it by 180 over pi. I don't have a calculator on me, but
And cancel the pi's, and then 6 3 times and 0. There you go.
okay. 13.
Wait, radians in degrees, radians to degrees, degrees to radians. I think
Is
radians
the
to
other way around.
yes.
Okay, so it's pi. Okay, so when you're converting degrees to radians,
Oh
you'd
yeah,
have to
yeah.
times.
180 over pi. No, no, this is correct. Yep, that's right.
Okay. Okay.
So
So wait, just to get it right then. So when you're converting from radians to degrees, you do it like this. And then if you're doing degrees to radians, pi over 80.
yes, that's right.
Okay.
Next, linear
180.
speed. Yes. Are we good to move on?
Yeah, yeah.
Okay. Linear speed. So linear speed is v. Okay. A motorcycle of mass 50 kilograms on a circular racetrack is 10 meters per second. The radius of the racetrack is 500 meters. What's the centripetal force?
Okay, so centripetal force equals mass times acceleration, and acceleration is uh, r omega squared, like
Yep,
all of them squared,
yep,
um, over time, or
yep.
right, no, radius, sorry. Um, so now, let me see. Oh no, we already have the speed. So it's just 10 squared over 500 times, yeah, exactly that.
Yep.
10.
Right.
Okay.
Excellent. Yeah, that's really good. So since acceleration has two formulas, if you have omega given, try to go for the omega squared r formula. But if
Yeah.
you have v given, we'll go for this one. Right?
Okay. Yeah.
Perfect. Let's move on to the next one. An athletic hammer consists of a heavy metal ball on the end of a steel wire, which is rotated around an athlete's head before being released. So you could just again think of like a metal object and like a string. Okay. So angular speed obtained by training hammer thrown in a competition is this. So you have your angular speed given. The combined length of the steel rope and the athlete's arm is this. So this would be your radius, right? So the
Mm-hmm.
athlete is swinging this hammer or this string and metal ball, and the arm of the athlete will be counted in your radius. So the radius will be this total thing, right? Radius. The
Yeah.
combined length of the steel rope and the arm is 2 meters, which is your radius. What's the centripetal acceleration?
So we know the acceleration is v squared over r,
Yep.
and v squared equals to r times omega.
Yep, that's good.
So we do 2 times 2, which is 4. Uh, oh no, yeah, sorry. We do 4 times,
Or could we directly do omega squared
or
r?
we can do, yeah, we can just do 4 then.
Yep.
4 times, is that it? Is it just 4? Wait,
Yes.
what?
Yes. So omega squared to 2 times 4 into the radius r, 8. So basically, if
Okay,
v squared r, v squared over r, v is r omega, right?
yeah.
So this v is r omega, and this whole thing is being squared. And there's one r at the bottom. So you can cancel one r with one r. So you have omega squared into r, right?
Hmm.
Omega is 2, so 2 squared is 4. Into the radius r is 8. 4 2 times 8.
Yeah, yeah, yeah. Okay, yeah, makes sense. Yeah.
Okay, perfect. Let's do a difficult question. Um, okay. This is not difficult, but it's a little conceptual. Let's do this one. So, a mass is swung on a string in a circle of radius r. The string breaks and the mass continues to move. Which line in the table shows or describes the motion of the mass in the horizontal and vertical dimensions? So, this string breaks and this mass is going to move somehow.
Yeah.
What's the horizontal and vertical motions? Horizontal, does it
Oh,
move in a circle? Does it move?
no.
No, it doesn't. Yeah, that's right. Does it move in a circle of radius more
No.
than? No. Is there no horizontal motion?
Uh, no, there is.
Yes, there is. Otherwise, it would just be
There's
going up or
D.
down. Yes, that's right. It moves in a straight line at 90 degrees to the radius. Just remember that whenever your centripetal force disappears, if the string breaks, there's no more centripetal force. If the centripetal force disappears, the object will move tangential to the circle. Okay?
Yeah.
So
Okay.
it moves in a straight line at 90 degrees. A tangent to the circle is always at 90 degrees to the circle. And it accelerates downwards. Of course, we know it's going to move like down like that. So it accelerates down like that. All good?
Yeah.
Okay. So let's do this. A question for momentum.
Hmm.
So a car drives into a wall. The change in momentum is 1700 kilograms meters per second. So this is your change in momentum.
Yeah.
And the time of impact is zero point 0.1 second. What's the force acting on the car as a result of the collision?
Okay. So we know the equation for change in um, change in momentum.
Yep,
So it's difference in so it's mv. Um, it's sorry. It's change in momentum over change in time, which will give us the average force. So um, we already have momentum, which is 17 thousand over time, and time of impact is zero point 0.1. So it's yeah, zero point 0.1, and that should be like the force. That's
excellent. So 170,000 part C. Perfect.
yeah.
Mm, I think I'll skip these. These are pretty simple. Let's do an advanced question. Let's do this question for free body diagrams and other concepts of forces. So this question is pretty good in a way that it covers a lot of concepts.
Hmm. Uh,
Yes. Okay, so the diagram shows a block of mass 2 kilograms sliding down a rough slope from rest against a constant friction of 2.5 newtons. So this is your friction. I would highly recommend just highlighting the important information. So this is your mass M. It's sliding down a rough slope, so there is friction, and it's starting from rest. So your initial velocity would be zero, right? Whenever
yeah.
I see rest, I like to put initial velocity zero just in case I need it later. So use the following assumptions to help you with the calculations. You can take acceleration of free fall to be 10 instead of 9.81 if you need it. Cosine of 20 is 0.9 and sine of 20 is approximated to be 0.3. So what's the momentum of the block along the slope after 5 seconds? So time is given to you and you want to know the momentum of the block.
Okay.
I'll give you a minute to think about it and then we'll take it.
Yeah. Okay. So we're given the mass, the friction. So friction, the friction is the force, right?
Yes.
So we can we do Ft equals change um in momentum, and then we kind of like, can we do that? Is that the one we have to use?
You are on the right track, but note that this force is your net force.
Okay, yeah. So
Friction is one of the forces. You'll
yeah,
need
yeah,
to draw a free body diagram here. So I'm just gonna look
yeah.
at the
Okay.
okay.
Okay, wait. Let me actually let me read it one more time because I think I kind of rushed that.
Yes, sure.
Um.
A hint I can give you is look at
Mhm.
all the forces that would be acting on the block.
Okay. Well, you have friction going in the opposite direction of motion. So weight would be one of them. Normal would be one of them.
Yes.
Um, and then that's it from what
Yes, you
I'm
are on it.
writing.
Excellent. So the block is moving down, so this should be the direction of motion. And that tells you this would be the direction of your frictional force, like that, right? Now,
Yeah.
where does the forward force come from? You're not pushing it. So what do you think? Where does this come from?
Horizontal weight force.
Excellent. Perfect. That's
So
nice.
I would say, yeah, we should probably find that first.
Yep.
Um, so if weight equals the mass is what was the mass?
2 kilograms.
So 2 times, can we round to 10?
Yep.
So 20 is the kind of the hypotenuse, right? Or like the yeah, that oh that's it? Okay.
Yep.
Um then we have something. So the angle is 20 degrees. So it's wait, one there. Okay. It's sine of 20, right? Times it's which is 0.3, right?
Yep. Excellent. You are
So
right.
so 0.3 times
Time.
mass. No,
Hmm.
sorry.
So yes, you're on the right track. You take the weight component and then you have this component and
Yeah.
this component, right?
Yeah.
The horizontal component, this one, is going to be your hypotenuse sine 20, right? So hypotenuse is 20. So this would be 20 sine 20, right?
Yeah. Yeah.
This is 0.3. So 20 into 0.3 is 0.6 or 6, not 0.6. Sorry. It will be 6 newtons, right?
Yeah. Okay.
And friction is 2.5, I believe. Yes, 2.5. And the block is sliding down, right?
Mm-hmm.
Your
Yeah.
net force will be the
3.5.
bigger, yes, the bigger force minus the smaller one. 6 take away 2.5.
Mm-hmm.
So 6 take away 2.5 is 3.5. So your net force is 3.5. And then you'll just do multiplied by the time taken. The time taken is 5 seconds.
Yeah. Okay.
17.5. Oops, what happened?
Wait, but don't you divide first by 2 to find the acceleration on the slope?
Um, so basically what I'm doing here is I'm using this formula that you suggested. Ft is equals to change in momentum.
Yeah.
Your net force F is 3.5. Are we good? So are we good with that?
Yeah.
And then your time taken is 5 seconds. Are we good with that?
Yeah, yeah. No, okay, yeah, yeah. Sorry. I forgot the equation I proposed at the start because I was talking about like so for example like you divide 3.5 by 2 to like you do net force divided by mass to find acceleration
Okay.
uh, and then you times acceleration by 5
Mhm.
uh, and then you times whatever that number is to like which is now velocity
Yep.
by the mass to
Mhm.
find
Yeah, that
to
sounds
find
good.
the
Yep. It's pretty much the same thing.
yeah
Um,
yeah
if you want to. Now, one important thing I want to ask is that this
But yeah.
17.5 is the change in momentum,
Hmm.
but they asked you the momentum after 5 seconds.
Okay.
Is
So
it
you, I, uh, after 5 seconds? I mean, after 5 seconds, that's already, I mean, the end, right? So it is kind of like the change in momentum. I don't know.
yes, that's right. Because momentum change is final minus initial.
Yeah.
And since your object was at rest initially, its initial momentum was 0, right?
Yeah.
So this
So
term
it's
was
just
0.
17.5 minus 0, which is still
Yep,
17.5.
yep, that's right. That's your final answer for this one. Let's move on to, let's do, all right, I want you to think about this question now.
Okay.
A simple pendulum, a simple pendulum consists of a bob of mass m at the end of a light inextensible thread of length d. The bob swings through point y with velocity v and comes to an instantaneous rest at point x, where the string is just stopped. What
Okay.
the tension in the thread as the bob passes point y?
What is the time? Okay. Simple. Okay. When it comes rest at point X, does it mean it's like caught again? Like if it's, is it dropped from X or it's just okay. Just
Mm, So think
um
it like the bob swings through point y with velocity v and comes to instantaneous rest at point x. So
okay.
you could think of it like that.
Well, the tension, okay. The tension would be like the opposite force of like the centripetal force, right? Or no? It's is it not just the centripetal?
Yes, the tension is the centripetal force.
Yeah, because it's just going like, I don't know how to explain it. It's just like that's like how tension works. If like there's weight going downwards, then tension is going upwards in
Yep,
equally. Like is
yep, like that. And in this
yeah.
case, weight is still down, but tension is like that.
Uh, so would in this case would it be centripetal force or weight, or is it both?
And sorry, repeat your question, please.
So all we have to do is find centripetal force, right? Or like yeah, but isn't centripetal force the tension?
Not in at point y. So
Mm,
at point y, your centripetal force is going to be the net force, right?
mm-hmm.
At point y, your centripetal force is the net force. So basically, your centripetal force is going to be the tension take away weight,
Mm-hmm.
right? And weight is mg. So you want the tension, right?
Yeah.
So you'll do centripetal force plus the weight is your tension at point y.
Okay.
This is
Uh,
2 plus the centripetal force is Fc, and let's see some other information.
So ba um wait, let me okay, no. Okay, I get it. Yeah, I get it.
So tension take away weight is your centripetal force. And what's the formula? Can you recall the formula for centripetal force? It's M,
M times V squared over R.
and R in this case is the distance d, right?
Yeah.
Plus mg is our tension. And okay, I don't think we've covered this formula, but it's a good point to introduce it. We know that we know this law of conservation of energy, right? We will see this in the next chapter as well. But the law of conservation of energy, we've studied this in IGCSE as well, that energy cannot be created or destroyed. It only gets converted from one form to another, right?
Yeah.
So if you consider this to be the level ground, okay, the higher you go above the surface level or this apparent ground, the more gravitational potential energy you have, right?
Yeah.
And so at point X, it has gravitational potential energy mgr or mgd, right?
Yeah.
Basically, let's write mgh for now and I'll elaborate on that. So it has mgh. And when it's momentarily at rest, right? It's momentarily at rest at the top. So all of the energy is gravitational potential energy. And then it comes back like that, right?
Yeah.
So when it comes back like that, at this point, it's on the ground, so there is no more gravitational potential energy, but it's at its maximum speed, right? So
Hmm.
all of that gravitational potential energy gets converted to kinetic energy, right? So
Yeah, yeah,
basically,
okay.
yeah, all of the gravitational potential energy is converted to kinetic, and you put their formulas equal. So you have mgh is equals to half mv squared. You cancel the m's out, and you can rearrange this formula for v. So that would be, this 2 goes to the other side, you have 2gh, and then this square gets canceled by a square root. So v, sorry, it's getting reconnected. So v is root 2gh, or v squared. Since it's a v squared here, I don't need to remove the square root actually. So let's just do v squared is equals to 2gh. Are we good so far?
Yeah, okay. I
So
get it.
I will plug that in here, 2gh, and your h is just this maximum height, and it's this one, and it's the radius of the circle, d. Is that correct?
Mm-hmm. So you just cancel them out?
So you just do 2gd. And then I just plug this, sorry, v squared.
Mm-hmm.
I
So
plug
you,
this v squared in this equation.
yeah.
So I have m multiplied by v squared is 2gd over d. So the d's
Mm-hmm.
cancel out, plus mg is your tension. So 2 mg plus mg is 3 mg.
3 mg. Okay. Okay, this was quite hard, but I get it. Like,
Yeah.
okay.
It's just like connecting different formulas. It's once you see the connections, it should be pretty okay. But this was the new addition that I wanted to.
Okay.
All right, any questions?
No, no. That's
Would you
it.
like me
Yeah.
to go through this once again, or are we good?
I don't have time. I'm probably already running late, so
Okay, I'm so sorry. All right, I'll see
no
you
problem, no problem.
next time. All right, take care. Bye.
Okay. Bye bye.